In everyday conversation, an error and a mistake are exactly the same. They describe a moment where something goes wrong, leading to an inevitable collapse. But in the context of statistical data analysis, treating these two terms as interchangeable is a critical operational failure. A rigorous analyst understands that true statistical rigor does not mean eliminating all uncertainty from a dataset. In fact, perfect certainty is rarely possible. Ignoring this reality leads directly to the precision fallacy, the dangerous practice of hiding inherent data uncertainty behind mathematically exact decimal points. To operate effectively with data, you must draw a strict line of demarcation. You must separate preventable human mistakes from inevitable statistical errors. We are going to map the 3 unavoidable sources of statistical error and then dismantle the dangerous illusion known as spurious accuracy. Mastering this taxonomy is the foundational step for professional data handling. It is the dividing line between a novice spreadsheet user and a rigorous statistician. In statistics, the term mistake has a narrow, specific definition. Mistakes are the direct outcomes of human oversight, negligence, or carelessness. They typically originate during the mechanical phases of an investigation: improper coding, flawed computations, or incorrect raw data entry. Consider a standard transcription scenario where an investigator is tasked with manually copying physical observations from raw tally sheets into a digital database. During this process, the investigator looks at a valid recorded observation of 25, but unconsciously types the number 52. This is a mechanical human failure. It has nothing to do with mathematical variance. Because of this, we arrive at the cardinal rule. Unlike errors, mistakes can be completely eliminated. Proper training, diligent supervision, and cross-checking can drive the mistake rate to absolute zero. Because they are entirely preventable, the presence of mistakes in a final dataset invalidates the investigator's professionalism, not the underlying statistical methodology. Preventable mistakes stand in sharp contrast to the precise technical definition of a statistical error. This diagram illustrates the mathematical definition of statistical error. It is the fundamental difference between the true value and its estimated value. This gap is not a fault. It is not a failure on the part of the data scientist. This gap is an inevitable mathematical consequence. Statistical surveys rely on small sample observations. They do not possess omniscient, perfect data on an entire population. Furthermore, the everyday processes of calculating averages or compiling aggregations inherently require approximations and rounding to function. Novice analysts often assume that applying more complex math or feeding the data into better algorithms will eventually eliminate statistical error entirely. It will not. Refining your instruments or significantly increasing your sample size will absolutely minimize the error gap, but generally that gap cannot be reduced to zero. Accepting this baseline of variation is a prerequisite for valid, honest analysis. Error is built into the mechanics of sampling and approximation. Acknowledging its presence is a marker of scientific reality. Hiding it is professional malpractice. During an investigation, these unavoidable statistical errors generally stem from 3 distinct sources. The first category is errors of origin. These derivations are caused by the physical limitations of measuring instruments, or the inherent bias of the investigator collecting the data. Attaining absolute precision for real-world variables like height, weight, or distance is nearly impossible. The physical world resists perfect measurement. The second category is errors of inadequacy. These relate directly to the mechanics of sample representation. This occurs when a sample is improperly selected, or when the sample size is simply too small to carry the required data. Look at this population model. A poorly constructed sample of 100 people fails to perfectly mirror the complex demographic gradients of a city of 10,000. When you analyze this improperly selected subset, the resulting characteristics will fail to reflect the true universe being studied. The third category is errors of manipulation, which occur later during the data processing phase. These are the mathematical deviations unconsciously committed when an investigator measures, counts, or rounds figures for classification. These 3 forces, origin limits, sample inadequacy, and mathematical manipulation, constantly push data away from absolute truth. Flawless exactness in large datasets is a mathematical impossibility. Ignoring these structural errors leads analysts directly into the trap of spurious accuracy. Spurious accuracy is the presentation of a level of precision that is mathematically greater than the real, actual level of the underlying data. Take a case study where an investigator collects the ages of students. The methodology dictates that ages are measured strictly in whole completed years, no months, no days. Consider this calculation. The investigator collects 5 raw input variables, 16, 17, 16, 15, and 15. When we run these through a flawless mathematical average, the output resolves exactly to 15.8. That 0.8 is a severe warning. Because the original raw data completely lacked any inputs for months or days, this decimal is a statistical fiction. We must strike it out. The most accurate, justifiable statement is simply 15 completed years. Stating a decimal fraction here imputes a degree of precision that simply does not exist. The math is correct, but the statistic is highly misleading. We avoid this trap by adhering to the professional standard of reasonable accuracy. This standard seeks only the precision practically attainable and necessary for the objective. If you are weighing massive shipments of food grain in heavy quintals for large-scale logistics, recording the weight down to the exact gram is an unnecessary waste of cost and effort. Reasonable accuracy aligns your required precision with the practical limits of your data. Spurious accuracy outright misleads the user, projecting a highly exact figure that your measurements cannot support. The goal of data analysis is not numerical perfection. The goal is analytical integrity. Statistical error is an inescapable feature of physical limits and sampling techniques. It is a known variable to account for, not a bug to be ashamed of. Projecting extreme mathematical precision onto limited data is a failure of professional analysis. The mandate is clear. Eliminate your preventable mistakes, map out structural errors, and rely on reasonable accuracy. Never let a flawless mathematical formula trick you into claiming a level of exactness that your raw measurements cannot support.